Hi everyone, and welcome to my channel. Up to this point, the digital logic circuits that I've covered are considered combinatorial logic circuits. And what that means is that the output level at any instant of time is dependent on the input level at that instant of time. So if we change the input, the output is immediately going to change. And this is a characteristic of a circuit that has no memory. So the output is not being determined by any prior state that the circuit is keeping track of. So as soon as you change the input, the output changes. So the next logic circuit that we're going to start looking at are flip-flops. And flip-flops, abbreviated FF, are circuits that have a memory characteristic. They can store a digital piece of information, meaning a binary 0 or a 1. So here's a simple example of a combinatorial logic circuit. It's just a single gate. This is a 7400. This is a quad 2-input Nand gate. So there are 4 Nand gates on this chip, and I just have one of the gates wired. So the output is just connected to this LED here, and if you recall, a NAND gate is low only when both inputs are high. For all other cases, the output's going to be high. So I've got the 2 inputs here are both high, and if either of them or both of them are 0, the LED lights up here. And you can see that as soon as I change one of the inputs, the LED lights or turns off. And that decision is based on the value of the inputs at that instant of time. It's not being based on something that's being stored that occurred in the past. That's a combinatorial logic circuit. Very simple one, but that fits the definition of a combinatorial logic circuit. So that circuit was just a basic NAND gate with 2 inputs. And if you recall, a NAND gate is low only when both inputs are high, and its opposite, an AND gate, whose output is high only when both inputs are high. So if we put the truth table down for both of them, we have 0, 0, 0, 1, 1, 0, 1, 1. This is 0, 0, 0, 1, and X naught, which is the NAND gate, is only low when both inputs are high. So this here is X equal to A, B naught. But as soon as you change any of these inputs, the output responds immediately, and that response, the output is responding to the change in the inputs at that instant of time. So with combinatorial logic circuits, the output levels of combinatorial logic circuits at any instant of time are dependent upon the levels present at the inputs at that time. And any prior input level has no effect on the current output because combinatorial logic circuits have no memory. No memory. So now we're going to introduce a digital memory element. Now most digital systems combine both a combinatorial circuit or circuits with a memory element. So here we have memory. And you have inputs that go into the combinatorial portion, and you also have, this is external, inputs, and you also have external inputs being fed from memory. So some information has been stored from some previous data collection. And so in combination with these external inputs, some decisions are made in the outputs of these combinatorial circuits, And those results get fed back into memory to be stored at a later date. And also, with the combinatorial circuits, they result in outputs that get calculated from these external inputs, the prior memory information, prior bits that have been stored in memory, and also you'll have memory that goes to the output or the outside world too, so you can see that visually also. So you have the combinatorial portion constantly producing outputs based on external inputs and also from inputs that were stored previously in a memory element. So now let's define the memory element. And a basic digital memory element is the flip-flop, also abbreviated FF. And by definition, we're going to say an FF is a logic circuit with two outputs, which are the inverse of each other. Here I'm calling these outputs Q and Q naught. You can use any letter. It could be X, X naught. But standard notation usually says Q and Q naught. So the FF is going to have multiple inputs, but its outputs are going to be Q and Q naught, and they're always the inverse of each other. So if Q is a 1, Q naught will be 0, and if Q is 0, Q naught will be a 1. They're always the inverse of each other. And you can build a basic flip-flop either using two NOR gates or two NAND gates, and then observe its properties, its memory properties. So let's take a look at how we can construct a flip-flop using either two NOR gates or two NAND gates. So we can build a basic flip-flop using two NOR gates. So if we have two NOR gates, what we do is we connect the output of each NOR gate to one of the inputs of the opposite NOR gate. So here this would go to connect to this output, and here this input from this NOR gate goes to the opposite output on the second NOR gate. And so this is NOR gate 1 and NOR gate 2. This is the Q output, and this is the Q naught output. And this input is called set, and this input is called clear. So what makes this circuit different from combinatorial circuits is its memory component. So we use the set and clear to determine the value of Q and Q naught. By the way, Q is considered the normal output. So when you usually reference the output of the FF, it's in reference to the Q, and of course the Q naught is the opposite. So this is the normal, considered the normal output, and this is considered the inverted output. But when you use the set and clear to set the value of the output, you can then remove that signal or change it and still remember that prior state. And that's its memory characteristic. So let's go over the truth table for this NOR gate FF. So this is a NOR gate FF. Now for reference, let's put the truth table for a NOR gate. So a NOR gate, recall the output is going to be high only when both inputs are low. So if this is A, B, and X, 0, 0, 0, 1, 1, 0, 1, 1, the output is opposite of an OR gate. So the output is high only when both inputs are low. And if you look at this, the controlling bit here is a 1. If there is a 1 on either of the inputs of a NOR gate, you're going to have a 0 on the output. It's only when both are low that you get the high output. So the truth table for the flip-flop will look like this. We'll have a set, a clear, and then an FF output. Now, if the set and clear are both 0, the flip-flop output is unchanged. And we'll discuss that in a second. If we want to set the Q, the normal output, to a value, it responds to a high level, a high. So we have a high on the set with a 0 on the clear. That will cause Q to equal 1. If we have a 0 on the set and a 1 on the clear, that'll cause Q to equal 0. And if we have a 1 on the set and a 1 on the clear, the output will be ambiguous. And I'll explain that in a second also. So let's look at the first condition with the set equal to 0 and the clear equal to 0, and why we define the output as no change. So with both the set and the clear equal to 0, let's start off with Q equal to 1. So if Q is equal to 1, this 1 gets fed back to the input of NOR 1. And we know that as soon as there's a 1 on either of these, that the output is going to be a 0. So here we fulfilled our definition of a flip-flop where Q is a 1 and Q naught is the opposite, 0. And this 0 gets fed back to the input of NOR 2, and we have a 0 on the clear, and a 0 will produce a 1, like we initially assumed or started with, and we have the 1. So this condition is filled. Well, let's assume that Q naught is 0, and something curious happens. So if this is 0, this 0 gets fed back to the input here of NOR 1. A 0 and a 0 is a 1. This 1 gets fed back, of course, to the second NOR. And as soon as we have a 1, that forces this to a 0. So you're thinking, well, how can it be two different states? It isn't two different states. What this is showing is that Q will be whatever has happened in the past. So if you put two zeros on the set and the clear, if in the past it was a 1, Q was a 1. If in the past it was a 0, Q was a 0. So no change. So if you put a 0 and a 0, Q is whatever it was previously set to, and it will not change. So when the set and clear again are both a 0, the Q output is whatever the output was set to in the past, and it stays there with no change. So I've written down the truth table again, and we've checked this state and verified that state. Now let's see what happens when we have set equal to 1 and clear equal to 0. So if we have a 1 on the set and a 0 on the clear, well, as soon as we have a 1 on one of the inputs to this NOR gate, that forces Q naught to 0. That 0 is fed back to the input of the second NOR gate, and we know that a 0 and a 0 on the inputs of a NOR gate is equal to a 1. So that sets Q. Now, when we're referencing a flip-flop, we're looking at the value of Q as a reference. That's considered the normal flip-flop output. And of course, again, Q naught is going to be the inverse. So we've checked this condition here as correct also. So let's see what happens now when we have set equal to 0 and clear equal to 1. So this is Q again. And we've got set equal to 0 and Q and clear equal to 1. So now we have set 0, this and clear equal to a 1. So this, of course, is going to make Q equal to 0. This 0 gets fed back to the first NOR gate, and a 0 and a 0 produces a 1. So here we've verified this condition here. Now let's take a look at the condition where set and clear both equal to 1. Now, we've defined a flip-flop as having two outputs that are the opposite of each other. So in addition to calling this ambiguous, it should be called illegal, because by definition, this doesn't fit the definition of a flip-flop. This condition is illegal. So now what happens when set is equal to 1 and clear is equal to 1? Well, these 1s force both NOR 1 and NOR 2 to go to 0. Well, right off the bat we have a problem, because by definition we're saying that a flip-flop has two outputs that are the opposite of each other. So by definition this is an illegal condition. But physically what happens is that when you go to set these at both 1s, one is going to get there quicker than the other. So these in reality will be, not equal, but one will be a 1 and the other will be a 0. And the same thing happens when you go to remove these signals, is that you're not going to be able to remove them at the exact same time, and whatever signal is removed or applied first in time-wise, the flip-flops will switch states, and either Q will be 1 and Q naught 0, or vice versa. But this is considered an ambiguous or illegal condition because it's unstable. And by definition, the flip-flop is going to have two outputs that are opposite each other. So I've wired up a simple NOR gate flip-flop on the Heathkit digital trainer, and let's take a look at its memory characteristic and see if this truth table applies. So here I've wired up two NOR gates in a 7402. And if we look here, 7402 is a quadruple 2-input positive NOR gates. So there are 4 NOR gates on that chip. I've wired up 2 of them. So I'm using these 2 NOR gates here. So pins 1, 2, 3, 4, 5, and 6 are being used. So here's the basic circuit with the pins connected. So pin 1 is the set. Pin 2 goes to pin 4 on the second NOR. Pin 6 is the clear, and then pin 5 feeds back to pin 1 on the first NOR, which is an output. So here I have the set and the clear controls right here, the control inputs, and these 2 LEDs here are Q and Q naught. So with these 2 switches down, there are 2 zeros on the set and the clear, but you can see here we have an output. So the Q naught output is high and Q is 0. And if I turn this off, it's not that it's remembering, it's just that the peculiarities with this circuit, not everything is coming up to voltage and the signals are not all coming up at the same time. In this particular case, when you first turn this on, this is the state that we have at random. We have Q equal to 0 and Q naught equal to 1. Now, if we want to set the output to a particular state, if we take a look, we want to set Q equal to 1, we have to put a 1 on the set. So this is the set input, and it should turn this LED high, and this will be the opposite. This is the Q naught, it'll be low. And there it is. Now you're saying, well, that seems to be just like a regular logic gate. Well, let's look what happens when the set input goes back to 0. Remember, 0 and 0 doesn't change anything. It remembers what happened in the past. So the present is we've set Q to a 1 and Q naught to 0. Let's put this down to 0 now. And it remembers what happened in the past. Q is 1 and Q naught is 0. It's holding that value for us. It's remembering that value. Now if we want to set Q equal to 0, we have to put a 0 on the set and a 1 on the clear. So here, this is a 1 on the clear. It's currently at 0. Let's see what happens with Q. Q is now 0 and Q naught is a 1. And what happens when we put the clear back to 0? It's remembering that state. We set or cleared the Q to 0, and it's remembered that value. Now the last value is an illegal condition because it's not reliable, it's ambiguous, and it doesn't fit our definition anyways of a flip-flop having two outputs opposite each other. So if we go ahead and put these, well, we get zeros, but if we go to 0, see what happens? I can't make these go simultaneously. One of these gets there quicker than the other, and that stronger one ends up getting set. So we have here in this particular case, the Q is a 1, and it's almost like tossing a coin. I think if I try hard enough, there, I've gotten this to be the opposite. But that's an illegal condition with this very basic NOR gate flip-flop and flip-flops in general. Because by definition, again, the outputs are opposite each other. Two outputs opposite each other. But you can see there I've demonstrated the memory condition that this circuit has. You can also build a flip-flop with NAND gates, but the topology and the truth table are just a little bit different. So if we have two NAND gates, with the set and the clear, it's the same when we have the input of one connected to the output of the opposite. In this case, this is Q and this is Q naught. You can see a little bit of difference there between the NOR gate flip-flop and also the truth table, set and the clear, and the FF. I don't know why I'm always forgetting the A output. Now in this case, the NOR gate flip-flop responded to high inputs, and the NAND gate actually responds to low inputs on the set and the clear. And also a difference is the one on the set and the one on the clear is the no change state. And if we want to set 0, if we want to set Q, we have a 0 on the set. So a 0 and a 1 on the clear, and Q will equal to 1, and a 1 on the set and a 0 on the clear sets Q to 0, and a 0 on and a 0 is the ambiguous setting or illegal state. And the reason for this difference is, if you recall, a NAND gate produces a low output when only when both inputs are high. It's opposite of an AND gate, which produces a high output only when both inputs are high. So we built two flip-flops with NOR gates and NAND gates, but those aren't actually the logic symbols for a flip-flop. The logic symbol just consists of a rectangle like this, and you have the set and the clear inputs, and the Q and the Q naught inputs. So this is the set, or S, and this is the clear, or C. And if you see here, there aren't any small circles on the inputs here. So this tells us that this is a NOR gate type of flip-flop. And incidentally, not surprisingly, this is called a set clear, or SC type of flip-flop. So it's a basic set clear flip-flop. And this particular one is made from NOR gates. And the NAND gate, since it responds to low levels at its inputs, it'll have a small circle indicating that it responds to lows. And this is the set and the clear. And again, the Q and the Q naught. And this is a NAND gate type of set clear flip-flop. So these are the two logic symbols for set clear flip-flops. And just to summarize, a flip-flop is a logic circuit that has multiple inputs, in this case only two, and we'll cover multiple input flip-flops in the future. But this is a set and clear flip-flop, and flip-flops have two outputs, and they are always the inverse of each other, and they have a memory characteristic where it remembers a prior output state. And you can set that state with the correct inputs on the set and the clear. And here we have the NOR and the NAND type of flip-flop symbols. So that covers your basic flip-flop theory. I hope you found this video interesting. Feel free to like, subscribe, and or comment, and thanks for watching.